Okay, and we're recording. So last time we were talking about Gauss's divergence theorem, aka Gauss's theorem, aka the divergence theorem. And a quick reminder of where this came from. The first thing we did is we understood flux as a quantity that we can associate to a region. Given a region, right, we can talk about, first of all, we can talk about what its boundary is. That was something that we had to kind of fine-tune last time, right? Because the idea was that we had to get an orientation notion of what does it mean to talk about the orientation on a boundary. And then once you have the boundary well defined, then you can talk about flux through that boundary surface. Okay, so next step was to recognize that this flux quantity, boundary flux, for which purposes in this context, I'm just going to say flux because it's always boundary flux when you're talking about the divergence theorem. Flux is an accumulating quantity. And so you can take your solid, whatever your solid is, chop it up into a bunch of little itty-bitty, sub-solids, right? And the whole is the sum of the parts when it comes to flux. Okay, and that was a matter of drawing pictures and observing that whenever you have a shared boundary, the normals go the opposite orientation and they cancel. And then lastly, this right here comes from rewriting flux in terms of its corresponding density, right? And so the idea is that, because of the accumulation property, you can think of flux as being stuff-like. Obviously, it doesn't look like that and doesn't weigh anything, right? But you can treat it, it behaves mathematically as if it's stuff. So just to have a helpful metaphor, treat it pretend like you visualize it as if it's stuff. And stuff has location and stuff has density. And you can talk about how much of it there is per unit volume, and that's a computation, the details of which are less important than this perspective, my opinion. And anyway, the answer is that it's divergence. Okay, so altogether then, we get the resulting theorem right here, that boundary flux is a triple integral of divergence. Okay. All right, and we talked through this example. The big thing to remember, there's several big points up here, of course. I'm not going to repeat the whole thing, obviously, but the one thing that I'm going to take a moment to emphasize among the many important points discussed here is don't forget to think about orientations. It is a really important thing. And so S being the inward-oriented unit sphere, it is not a boundary. But if you look at the exact same surface, just outward-oriented instead of inward-oriented, that is a boundary of the ball that it contains, orientation and all. And so that blue surface oriented the outward direction is one to which you can apply the divergence theorem. The green surface is not. It's got the orientation is wrong. It is not a boundary of that solid on the inside. Okay. Everybody happy with that? Okay, so now I have some physical examples that I want to talk through, and I think this is really helpful for a couple of reasons. One, sure, it's always nice to be able to think about how does math help you solve physics problems. That's not my primary motivation here. So my primary motivation is kind of the opposite. Physics here, the physical world and how certain scenarios come up have the ability to help us with thinking about the math. Seeing how these physical examples work out will help you digest some of the math ideas that I've been throwing at you. So that's really my primary incentive here. So first one I want to talk about is a light bulb. And I like this because it's relatable. Right? We've all seen light bulbs. We kind of know what light bulbs do, and this is not in some sense, unrelatable, hard to imagine things like magnetic fields. That's weird. Okay, so very relatable. What do light bulbs do? They generate photons. Photons are the little particles that carry light. And I make the observation that this is a flowing fluid because, it's a bunch of little tiny particles that are all kind of moving together, if you will, at least in this scenario that I have here. Okay, so so we're going to think of this as a flowing fluid. Now, recall that when you represent a flow of a fluid with a vector field, you have to keep in mind, wait a minute, what exactly does the vector field represent? Does it represent velocity? Does it represent density times velocity? Is there some other version for some other reason? What are we doing here? And in this case, we're going to talk about density times velocity. And that's why these vector fields are, this vector field here is not constant. We have a longer field line there and a shorter field line there, not because the light is slowing down, right? But because it's spreading out and becoming less dense. There's fewer photons per unit volume out here. So density is lower. Whereas close to the light source, well, there's a ton of photons in there. That's just, they haven't had a chance to spread out yet. Okay. All right, how are we doing? Okay. By the way, if you want to know specifically what is this vector field and, how would I go about writing it down, one point of view you can take on that is that in some sense how spread out the photons are goes with the area. Because if you ask the question, for example, you take this sphere here, you got how many photons are spread out over this area? Well, all of them, right? All the photons that come out of the light bulb, they all hit this great big sphere. Versus if it was a smaller sphere, how much flux is there through the smaller sphere? Well, all of it, all the photons go through the smaller sphere as well. Right? And so the area of the sphere expands with radius squared, and so the density of photons decreases with radius squared. So that's one point of view that you can take. Punchline, though, this vector field is inverse square radial. I'm going to write that down here. This is inverse square radial, and we've talked about that vector field previously, and I'm going to do a callback to that point in a little while here. Okay. All right. So now, again, just to be clear about what's going on here, there are different kinds of fluids, and we have to always be careful. What kind of fluid is this, and what does it do? And so we've already talked about this is a fluid that's being generated. There is not a finite supply of photons, and we're just keeping track of how they move around. No. Very importantly, we are generating photons here. Right? This is a generated fluid. The other thing to note, though, is that it has a density that doesn't change with time. And if you flip a light bulb, we got light bulbs on in this room right here. Are we collecting photons along in here right now? Any photon that goes in goes right throughout. There's no sort of collection. The density of photons is not increasing over time. We have a steady state flow of photons. That's another thing to keep in mind. Okay, so what I want to do now is ask a couple of questions about divergence. Don't forget what divergence is. Divergence is flux density. It's flux per unit volume. Right? So we're going to look at different little regions. We're going to ask how much flux is there through the boundary of said region, and then we're going to ask what happens if I divide by the volume of that region. Let's just play through a couple of scenarios. Here's one. Let's look at a small region containing the light source, containing the little light bulb. And I ask, how much flux goes through that the boundary of this little region containing the light bulb. This spherical surface here. How many of the photons go through that little surface, that little sphere? All of them. Right? Again, that's the nice thing about if you have any surface that contains the bulb, the flux. How many lumens is that bulb is all you need to know. How many photons is it producing? All of them are going to pass through your surface. So I'm going to call that a relatively high amount of flux. Now let's ask, though, what's the volume of this region? If I were to, divide that flux by that volume? Well, by assumption, by setup, this is a small little ball, therefore it is a small sphere that has a small volume. So we have a high flux divided by a small volume, and so on this picture, the divergence is very, very large. Right? So in the vicinity of where the light bulb is, the divergence is super high. Does that make sense? Okay. All right, now next question. Let's ask the same question, but let's just take this ball and move it over there. Right? So now, same questions. How much flux is there through this sphere? And I want to be careful talking about the flux. Do keep in mind that flux is an oriented thing, and there is a positive direction and there is a negative direction. The positive direction is outward. Right? That's what we mean by positive flux. So when I ask now, how much flux is there through this sphere, you got to keep in mind the signs, right? So when a photon gets shot out of the light bulb here, the first thing that happens is that photon goes inward into that sphere. That's not what positive flux is. That's going inward, not outward, right? Outward would have been positive flux. So photons going inward means that it counts as negative flux as it enters. And then, of course, it keeps proceeding, and then eventually it exits, at which point it's positive flux. So, well, here's the thing. We've already agreed there's no collecting of photons happening in here. The density of photons inside of this little ball is constant. The quantity of photons inside of this ball is constant. So the number going in and the number going out are the same. So the flux, I claim the flux here is 0. Right? Anything that goes in also goes out. So grand total flux is 0. How do y'all feel about that? That make sense? Okay, so what happens when you divide 0 by a small volume? Well, still 0, right? So over here in this area, and more to the point, anywhere else, so not just that region there, but anywhere other than where the light bulb is. Okay, I've bitten off more than I can chew here, coloring in wise. Everywhere other than the light bulb is, the divergence is 0. That makes sense to everybody? Okay. All right. So what? Who cares? What does this have to do with anything? This, the two little calculations that we've done illustrate a point that I've made previously, I think, really well. And that is that divergence tells you where the flux is happening. It tells you where the flux is coming from. And, previously, we talked about this as a kind of an abstract statement about, well, it's an accumulated quantity, and if I added up all the pieces and notice the cancellation, and then I've made appeals by analogy to fundamental thermocalculus, etc. But here, you can absolutely see it, right? So let's look at this surface here. There's a flux there, certain amount of flux happening on that surface. Where's that flux coming from? Well, it's coming from where the photons came from. It's coming from the center, where the divergence is pointing. Right, the divergence is huge where the bulb is. Right, so that it's saying right here, by virtue of the divergence being large, it's saying that's where this flux is coming from. Literally coming from the inside, not coming from. We're measuring photons as they go through the surface, but they're not coming from the surface. That's just where they happen to be where we measure them. They're coming from the bulb. Divergence is pointing right at it. And how much of this flux? Let's see here. Let me color code this, by the way. Divergence is huge. There. How much of this flux is coming from around here? None. There's no photons coming from this green region. They pass through the green region, but that's not where they came from. Everybody see what I'm talking about? So this is, again, so the purpose that this serves, my goal here is not for you to understand light bulbs better. My goal here is for what you already understand about light bulbs to help you get comfortable with the idea that, divergence really does point to, it's telling you where the flux is coming from in a very meaningful and natural sense. Let me pause here. How we doing? You buy it? Everybody happy? Okay. All right. Now, here's a different physical example. This one is not only superficially different, this is also qualitatively different in an important way. So I want to talk about gas. So there's no light in this example. We're going to talk about a quantity of gas. So we have a gas cloud somewhere. And I'm going to talk about this scenario of the gas kind of moving radially outward. And the metaphor that I have in mind when I wrote this example and that I think is the easiest to relate to is, let's just imagine that it's like a gas cloud out in space. I don't want to have to worry about gravity or anything like that. And then let's suppose for whatever reason the temperature starts to rise. And y'all may recall from high school physics that when you have a gas, if the temperature rises, then the volume increases. Right? And so, now let's just imagine if you've got the gas and if it starts to expand outward like that, the gas is therefore flowing kind of outward. Does that make sense to everybody? And I claim that this is what the vector field would look like, representing that flow. And that's what we have pictured here. It's a little counterintuitive. It's tempting to say that, isn't all the gas doing the same thing? Not quite. Because the thing is, the gas in the middle is expanding. Yeah, sure. But the gas that's over here near the edge, it's doing two things. For one thing, it's expanding in the same way that this gas is, but it's also, the whole thing is being pushed by the gas closer in that is expanding. So in some sense, the farther you are out, the more gas there is from the middle, all of which is pushing you as you are also yourself expanding also. So that's a physical case as a sort of a for why I claim that this is a reasonably plausible model for what we're describing. Okay, so everybody happy? And obviously, if you have a fixed amount of gas and it's expanding, the volume is increasing, then the density is decreasing. Okay, so here's the thing. That's one of the big differences then with the light bulb metaphor. And let me, you know what? I erased something I didn't want to erase there. Let's see, let me get rid of all this. Big difference. The density is decreasing here. Not so with the photon story. With the photon story, the light bulb story, photon density was not changing over time. Here, the density is absolutely changing over time. This is a very different kind of a fluid flow. And here's another big difference. Here, photons are being created. They're being generated over time. Not so here. Right? When we're talking about this nebula, right, out in space, a big clump of gas, that's a fixed amount of gas. There's no gas. No gas is being generated. It's just warming up and expanding. Same amount of gas. The gas is fixed. So very different scenario, I guess I'll say. Does everybody see those big differences? Questions? Feel free. All right. Okay, so so let's play through this, see what happens. So here's the divergence theorem, and by the way, you can compute this divergence. The divergence ends up being 3K. Don't forget your vector field. You put in there, and we've got a formula for how to compute divergence, and if you write that down, good exercise, everybody should do this. It'll take you 15 seconds, it's no big deal. But if you compute the divergence of that vector field, you get 3K. Okay, so what does this mean then? And the idea here, by the way, this is the divergence theorem as applied to this region, this ball. Right, so when we say flux, we're talking about flux that's on the boundary. And that's a measure of, well, if you think about it, again, this vector field is representing the flow of a fluid, and if we're looking at the flux through this boundary, we're looking at gas that is departing outside of this region, right? And so we're talking about the rate of flow of quantity, mass of gas that is passing through the region and therefore out of the solid. Is that cool? Okay, so where's that flux coming from? And what interpretation do we make of that? And again, you can, there's different points of view you can take. If you want to be rigid about it, you can say where the flux that comes from gas passing through the surface. Well, the gas, little particles of gas, they are literally right there as they pass through, right? But again, to a large extent, gas that's right here that gets pushed through the surface, to a large extent, is being pushed by stuff that's happening in here. It's the fact that there's an expansion happening on the interior that's doing the pushing, that's pushing everything else out through it. Right? And so the take that I would give is that the reason we have flux is because in little regions where there was a certain amount of gas, that region got bigger. That pushes other gases, and by virtue of it getting bigger, that's what's pushing the gas out the sides. And we can see exactly how much of that is happening by looking at this integral. Right? So altogether, this flux that we see on the boundary, gas that's leaving through the boundary of this solid, divergence constant says that, really, morally, this flux that we're seeing on the boundary, it's kind of coming from everywhere, because everywhere throughout this interior, the gas is expanding. Right? The density is decreasing, that's increasing volumes, that's pushing gas outside of our solid. And so this is a way of kind of measuring, the rate at which density is decreasing throughout your interior. And the fact that this is a constant here is an indication that that density is decreasing at a constant rate everywhere throughout our interior, which again, physically plausible, right? If the temperature is increasing at the same rate, temperature increasing is what causes volume to increase, which is what causes density to decrease. So it's a very different physical metaphor, right, for divergence, and maybe it's relatable in a different way. You might like this one better, you might like this one better, but they're both physical examples of what divergence kind of looks like in some sense. Okay. All right. Now, last thing I'm going to say about fluids is that both of these examples are kind of what you might call extreme examples of what is actually kind of a spectrum. So, on the one hand, we had purely generation of a fluid, right? If there was a flux, that flux happened because that fluid got created. Okay. In our second example, there was nothing being created. There was no generation of fluid. Right? In our second example, we just have the expanding gas. Flux is a consequence of density changing. Decreasing density means it's that mass that had been in there is either itself leaving or pushing other fluid to leave. But then there was no generation, right? With our gas example, there was no gas being generated. So these are sort of the extremes. In general, though, you could have both of these things happening at the same time. And the way I like to think about this, I like to start from sort of a global perspective. So all together in your entire scenario, if there is generation of fluid at all, let's just say, to whatever extent fluid is being generated. Well, there's really two possibilities on what can happen. When you create fluid, it either stays in your region, in which case the quantity of fluid increases, or it doesn't stay in your region, and if it doesn't stay in your region, well, it had to leave. And if it leaves, then it leaves by way of passing through the boundary. And if it passes through the boundary, then it's flux. Right, so this is the two possibilities. If you make stuff, it either stays or it doesn't stay. Right? So anyway, so the point being that when you have a flux, you can interpret that flux as, well, look, maybe that flux is it's some combination of either the total quantity of fluid is decreasing, or the fluid is itself being generated. And of course, there's a minus sign because you're going to move this to the other side. And fluid leaving is a positive flux, but it's a decreasing quantity, so there's a minus sign in there. That's why it's on this side of the equation. So you could have both in play at the same time. Okay, and we're not going to go into examples of where you have both in play at the same time. This is a little bit of sort of foreshadowing. Y'all may see this in a future context when you're using the divergence theorem to understand fluids. And so I just wanted you to sort of have the heads up. And then real quick, if you just take this equation here and divide by volume, pretty much, then if you think about it, flux per unit volume is divergence. Mass per unit volume is density. And, well, now, this, generation rate, total quantity, mass per unit time that's being created. You can ask, where is it emerging? Where is it being created? And so, how much of that there is per unit volume, I'm going to call that generation rate density. If you come back up here to the light bulb example, there's a lot of generation happening there. The generation density, generation per unit volume where the bulb itself is extremely high. And out here, what's the generation rate density? It was 0. There's nothing being generated at all, per unit volume or otherwise. Okay. All right. So again, this is just for your possible future interest. Is everybody okay with that? Okay, here's another example. Gravitational fields. So this is my physics history showing a little bit. I think, though, that there's a really nice punchline to this. This is a fantastic metaphor also for divergence. What does divergence look like? Where does it come from? How do I relate to it? That kind of thing. What does it look like? So here's the scenario. Let's think about gravitational fields. We've already talked about point mass gravitational fields, and they look like this. Again, we call this inverse square radial. We call it inverse square radial because, of course, one of these factors in the denominator is what goes to making this a direction, a unit vector. And so in terms of magnitude, it's really literally inverse square. Not inverse cubed as it might look at first glance. Okay, so inverse square radial. Oh, hey, wild! We've heard that before. When you have a light bulb, the corresponding, a point light source, not a point mass, but a point light source, inverse square radial. So that's pretty weird. Gravitational fields look just like photon flow fields. And whenever there's a coincidence like this, that, oh my gosh, these two physically totally different things look exactly alike, then people start thinking, maybe it's not a coincidence. Maybe there's a natural reason why. And there is I'm going to call it a point of view Some people would call this a theory, I think. And by the way, let the record show I'm not a professional physicist, and the particulars of what I'm going to talk about here are, I'm going to hesitate to state anything as fact. And I think there's certain theories. Some of this is theory. Some of this is just, well, a point of view that you can take. But what the current status of, is this theory in favor? No comment. I'm not going to comment on that. But that said, if gravity communicates from a formula standpoint, gravity communicates just like photon flow fields do. Maybe, just maybe, gravity is actually, just like light, is communicated by emitted particles. Let me say it differently. If gravity were actually communicated by little emitted particles, they call them gravitons, little emitted particles created by mass, how would you tell any difference? Right? And, if it was emitted particles created by mass, just like light is, then the vector field would be exactly that. It would be exactly what we observe physically. So, it's another one of these situations where, whether it actually does or doesn't, are gravitons actually real? That's, it's an interesting question for physicists to worry about. But as far as we're concerned, you can pretend that they're real and everything's going to work perfectly. Right? And so, I think it's a really nice metaphor. And this is how I tend to think of gravitational fields, is that they are a flow of gravitons. That makes sense to everybody? Pause for questions. Okay. All right. So now let's see here. I am going to kind of draw a little bit of a line there. This calculation that I've got down here is a different scenario. The picture that I drew up here was of a point mass, right, and the gravitational field, aka the flow of gravitons created by that single point mass. And what I'm going to do now below the line, totally different. Below the line, I'm going to assume that I have a distribution of mass. Right? So back to the real world in some sense, right? This idea that there's going to be a single geometric point at which there's a bunch of mass and then there's no mass anywhere else, that's not really how things work, right? So suppose you have mass that's distributed. This first equation here, aside from this common factor on either side of negative 4 pi g, this first equation just says mass is a triple integral of mass density. So that's an uncontroversial statement. This is old news. Mass is a triple integral of mass density. Well, of course it is. And then I multiply through by negative 4 pi g for reasons that I'll kind of explain in a moment. But again, legal, because I did it on both sides. Okay. All right, everybody okay with this? Mass is triple integral of density? Okay. All right, so now having done that, let's look at this here, and the claim that I'm making is that this is equal to the flux, the gravitational flux. Now let's talk about gravitational flux for a second. It's a pretty weird concept if you think about gravity in the usual way. In the usual way, you think of gravity as representing, forces. Why would I do a flux of forces? That's weird. We've talked about fluxes of flows of fluids. That makes sense in the context of flows of fluids. There's a surface. I've got a fluid. It's passing through the surface. How much fluid per unit time is actually passing through your surface? That's physically relatable. But forces, why would we ever be interested in flux of a force? It's hard to figure out what that ought to mean, but let me remind you, at this point, we are thinking of gravity as being a flow of emitted particles. So, flux, if you come along for the ride here, and let's think of gravity gravitational fields as being flows of gravitons, flux is very natural. Is that cool? Yeah, all right. So my claim is that the flux is proportional to the mass. And why should the flux be proportional to the mass? Well, just keep in mind, mass, let's see, I'll color highlight. Mass is what creates the flux in the first place. Mass is what creates the gravitons. So, you got more mass, well then there's more mass pumping out gravitons that, of course, then eventually pass through the surface, the boundary of whatever region you're looking at. Because after all, if you've got mass that's inside of the region and it shoots out a graviton, that graviton eventually leaves the region. Namely, that graviton eventually shows up as flux through that boundary. Everybody believe that? More mass, more flux. Because more mass, more gravitons, aka more flux. Okay. All right. Alrighty. So we started off with mass as an integral of density. Now I've made the observation that mass is proportional to flux. And by the way, that's the only reason we put this negative 4 pi g in here. That's just, you can think of it as just a units thing in some sense, but how many gravitons are being shot out by each, how much mass, and negative 4 pi g is the number that does that. That's all it is. It's no big deal. So what about flux? What else can we say about flux? Well, flux divergence theorem. Right, I'm just going to write this down, and that's a kind of a freebie. So here's the thing then. That means that these two integrals are equal. And this is a powerful observation. If these two integrals are equal, and keep in mind, these two integrals are equal no matter what region you're looking at. And how could two integrals always be equal no matter which region you're looking at? Well, that suggests that the integrands ought to be equal. And that's the big realization. That's the conclusion that we get here, is that divergence of the gravitational field. This is a physical interpretation of divergence. Divergence of the gravitational field is a measure of how much mass density there is there. And it's a consequence of these dots that we've connected by going around this little square of equations. Everybody okay with that? And I make the case that this is actually fairly physically plausible too, if you really think about it. If there's no mass, we know there's no divergence. Right? That's this picture we talked about over here. Inverse square radial. If you're talking about a flow of photons or gravitons, whatever. If you're talking about a flow of particles that were created here at a source, well, to what extent are they being created there? None. They go in, they go right back out. There's no divergence here because there's no flux happening here. Anything that should happen to pass through that boundary came from elsewhere. Came from here. It's created here. So nothing created there. And so I claim that makes sense with this equation. If divergence is a measure of how much boundary flux there is, then, in the sense of how much is being created in that general vicinity so that it shoots out gravitons in all directions, etc. Well, how much mass there is there per unit volume should tell you how much of that flux there is per unit volume, because flux is created by mass. Okay, you might say this differently as other than constants. Let's see here. Let me get the highlighter on. Other than constants, flux comes from mass. And if flux comes from mass, then flux density comes from mass density. I think that rolls off the tongue pretty nicely. Does that make sense to everybody? I'll say it again. That's a good one. Flux comes from mass. So flux density comes from mass density. So, yeah, okay. So, anyway, y'all have a pre-existing, really good intuition for mass density, right? Y'all have had a sense of things being, there's a lot of, this is a heavy rock heavy for its size. It's a high density, right? And low density, like a piece of balsa wood, is shockingly, oh my gosh, how could something that large weigh that little, right? So this idea of mass density is a relatable concept. And, well, if mass density is relatable, you've got yourself to that extent, you have a physical metaphor for what divergence looks like. Divergence is a measure of mass density in terms of how that's creating gravitational flux. Anyway, it's a point of view. It's also some good physics to know. Okay, electric fields. Here's the weird thing. Electric fields are also inverse square radial. So, yeah, it's totally different physics. Totally different physics, but it's exactly the same vector field. And so we get a lot of the same conclusions, right? So now this is, like I say, physically different, but other than this constant here, which is included for sort of unit purposes, and again, equal on both sides, so that doesn't matter. But charge is an integral of charge density, right? So charge density. I mean, again, this is, we haven't talked about charge, and we haven't talked about charge density previously, but in general, any quantity is an integral of its associated density. Okay? So I'm saying that charged particles, by the way, this is pretty standard notation to use Q for total charge and to use the letter rho. Unfortunately, it's the same rho from spherical coordinates. Sorry. But it's pretty standard. But rho represents charge per unit volume, aka charge density. Okay, so again, quantity is an integral of density. If charge were to emit a fluid of some sort, again, keep in mind, inverse square radial. So, per that metaphor, if you were to think of charge as emitting this kind of a fluid that communicates what we see as an electric field, right? Then the more charge there is, the more flux you're going to have of that fluid, whatever that weird fluid is. And I don't want to comment on how they describe this fluid because it gets a little weird, and I think it'd be counterproductive to talk about that. Anyway, same point that I make up here. Mass creates the photons that are the flux that you would measure on the boundary. Okay. So likewise, charge in this scenario creates the fluid, whatever that is, that becomes the flux through the boundary. And then, of course, here's the divergence theorem, just writing down the divergence theorem. And again, therefore, equating these integrands, because this applies over all solids, and we get an interpretation, this electric field context. Divergence comes from charge density. So this is morally identical. I'll say structurally identical. This equation about electric fields is just same mathematical underlying reality with a different physical veneer on top as this equation up here about divergence of gravitational fields. Which is itself a different physical veneer on top of the idea of, look, you have a light bulb that shoots out photons. Right, so same basic idea, just different physical examples. Okay, for whatever it's worth, this one goes by an important name. This is one of Maxwell's equations. Y'all may recognize if you had an E&M course. This is what I like to think of as the first of four Maxwell's equations. This over here, also known as one of Maxwell's equations, in fact, also known as the first these are considered to be morally the same equation. Just kind of different forms of the same equation. Because if you think about it, again, they're really saying kind of the same thing. This says flux comes from charge. This says flux density comes from charge density. Same statement, right? Just with the word density attached. This is per unit volume. This is global. But they're still talking about the relationship between flux and charge. In case you ever wondered why they have these different versions, why are these two equations that look so different in terms of how they're written down? This is about flux and charge. This is about density and divergence. If you say it that way, they don't seem like they ought to be related. But you see here that they are really very highly related. And I'll point out that the connection between these, unavoidably, right, is the divergence theorem. So it's a really big deal to understand the divergence theorem and to understand divergence as a quantity, as a concept, to be able to relate these physical quantities about electric fields. What do you think? Okay. All right. So if you've already taken your E&M class, then you might look back through and see if you can see signs of this big theorem that we're now learning about in that. And if you haven't yet taken it, or if you're taking it now and they haven't gotten to this yet, then good. You're going to have a huge advantage over everybody else. You'll see how it is that divergence is the thing that connects these two theorems, or these two equations, Maxwell's equations. And of course, there's many other ways that you're going to have big advantages there. Okay. All right. How we doing? Right. Okay. So we have, let's see how much time we got left here. We have 3 minutes. I'm going to just lay a little bit of groundwork, and then we'll call it a day. This is another big theorem in Chapter 7. It's another ripoff of ideas that we've already done several times at this point. Stokes' theorem is, it's just like the divergence theorem. It's just like Green's theorem. Different dimensional context. The divergence theorem, Gauss's divergence theorem, is about three-dimensional solids in space. Stokes' theorem is about two-dimensional surfaces in space. Not to be confused with Green's theorem, which is about two-dimensional regions, not in space. Green's theorem is exclusively about two-dimensional regions in the plane, in R2. Stokes' theorem, we're going to do something kind of like that, still two-dimensional regions, but in space instead. So yeah, it's got some things, the context has some things in common with the divergence theorem, and it has some things in common with Green's theorem. And it's going to be just kind of we're going to take all the same ideas and adapt them accordingly. So in particular, going back to Green's theorem, remember we got particular about what boundaries mean, talked about orientations, set an arbitrary but standard convention. Then we talked about the accumulation property and all of its corresponding consequences. And then we talked about the idea of the corresponding density. And then we made a theorem. Well, we're about to do exactly the same thing here. We're going to get particular about what boundary means. There's details to be worried about. We're going to talk about accumulation. We're going to establish that a particular quantity in question will accumulate. Then we're going to talk about the corresponding notion of density, and we're going to make a theorem. So we're going to do all the same stuff that we've been doing, right? It's really the same thing over and over again. Different details. Therein lies the devil, right? I mean, we're going to have to really pay attention to the details, but it's really very, very analogous. And that's a good place to leave it, and we'll call it a day there, ending a minute early. I'm sure I owe you far more than that. So y'all have a good break.